you, Professor Wang, for this very insightful and interesting talk. Moving on to the Q&A session is when we calculate ammonia as a carrier, the application terminal in the fuel cell, what if the produced ammonia is directly burned to generate electricity? Will the CO2 emission still be so high?
That's a very good question. So the analysis I just showed is to use ammonia as a hydrogen carrier. So ammonia combustion is a different story. Although first I want to mention is that ammonia combustion is still not very mature because ammonia is difficult to burn. So you typically need to co-burn it with say gas, natural gas, or even coal. And by doing so, you actually make the system more dirty. Why? Because we generate more NOx. And a recent study by MIT, by a research group in MIT, they provide analysis and claim that if we only replace the maritime fuel to ammonia, so we are not talking about the energy sector, we just replace the maritime fuel to ammonia, the world may experience 600,000 more premature deaths per year. So if we consider that for energy application, I think that the environmental impact can be even larger. And this is why I have reservation. In addition to cost, I think it would be very expensive. But environmentally, it can also be very dangerous. And therefore, I think the whole world need more detailed discussion. Thank you.
Right. Thank you so much for your answer. Moving to the next question. At what scale can formic acid dehydrogenation be applied?
That is a very good question. So as I just mentioned, that we have already completed the 20 kilowatt power generator prototype. And then the 40 gigawatt, 100 gigawatt is in the pipeline. But the good thing of fuel cell application is that it is modular. So that if we want to design a larger system, we just need the engineering integration like Lego. And this is why I believe even large scale application is possible. Thank you.
Thank you. On the next question. Why is carbon capture, utilization, and storage still being emphasized as a key solution then?
Capitalism. That's my answer.
Okay.
Capitalism.
Okay.
Yeah. So, but I think this is why I think the voice from the public is very important, because if something that does not have the real climate impact, how can it be exercised? That is because it has the money from the support from government. And when I say money from government, that's the money from taxpayers. Us, we are supporting this. So if we support the technology that cannot deliver the claimed climate benefit, we need to say no. And this is why I say, of course, don't just take my words for granted. I just want to provide different perspectives, and I encourage everyone to use fundamental thermodynamics, chemistry concepts to analyze these options and provide your own understanding. And if you also believe that this is a wrong direction and this is a huge destruction to our existing resources, make your voice heard. Thank you.
Thank you. Moving to the next question. What are the key economic or technological barriers to the widespread adoption of green hydrogen or biofuels, and even the technology of implementing formic acid dehydrogenation? Is it the catalyst cost, or is something else?
So thank you. So this contains many questions. Okay, this one contains many questions. First, is green hydrogen. Is green hydrogen useless? No, green hydrogen is very useful. I just say the hydrogen storage and transportation is a huge challenge. So, but we still need to produce green hydrogen so that we can decarbonize the energy, the hydrogen-related industry, then that is very important and meaningful. But I don't think hydrogen should be produced as a fuel because we don't have the viable process to store and transport them. And in addition to the potential risk that can come from fugitive hydrogen emission. So that's my view about green hydrogen. And then biofuel. I think biofuel is very important, particularly for places like South Asia, including India. You have huge amount of resources for biomass. And biomass is a biological way of direct air capture. So the carbon there is actually negative from the air, right? So if we use the biomass, the application for biomass is actually this carbon neutral pathway. So I would say biofuel is very important and we should utilize them. The only challenge is that its scale is small because biofuel comes from the process of photosynthesis, and photosynthesis efficiency is only 0.5%. So that is significantly lower than the state-of-the-art photovoltaic. So we are talking about 20%. So if we want to produce enough biofuels to decarbonize the energy sector, we will need to use 20 times more space. And don't forget, if we want to grow biomass faster, we also need fertilizers. So we will have to produce even more ammonia, and then that will also come with other environmental impact because when ammonia is applied to soil, it can be oxidized to N2O. N2O is 300 times greater than CO2 as a greenhouse gas. So all these together, I think biofuel is a very important field, and we must utilize them. But its overall impact in the global energy and then climate picture is smaller. So I think what we need to do is to largely deploy solar electricity, and then we will need to have a various of energy storage technologies to fulfill short-term, mid-term utilization, and then long-term, and then distribution, transportation, and I think that's hydrogen, and that has to be done by hydrogen carrier, and not hydrogen carrier. My choice is formic acid, and for formic acid, I would say I think our formic acid to power pathway processes technologies are considered quite mature, and we are ready to deploy, but there are still a lot of room for improvement to produce formic acid from renewable electricity. And that is, I think that would be the direction I would encourage everyone to participate, to contribute. Thank you.
Sorry to interrupt, Manas. So we can take a couple of more questions, and we have a lot more questions in queue. So maybe a good opportunity for our attendees to connect with Professor Huang over email, if that is okay with Professor Huang. Yeah.
Sure.
Please go ahead, Manish.
Oh, thank you. Yeah, so we'll move to the next question. How is the recyclability of the lithium-ion batteries? And do we have a vision for waste management created from such energy sources when used in a very large scale?
That is a very good question, very important question. No one have done this at has been done. And there were a lot of activities done in China. And I know in Singapore, there's also a startup. And I believe there must be some activities in India. And I think that should not have a lot of technical barrier. And we should be able to do it reasonably well. And of course, in the future, like I say, we will need to improve the design such that the recyclability can be enhanced. And if our technology, the technology I just mentioned, become viable, if we demonstrate that at large scale, and I think we can make significant contribution into the lithium recycling business. Thank you.
Thank you. With the last question for this session. Can hydrogen bonding or halogen bonding organocatalyst be designed to capture and activate carbon dioxide?
Yes, yes, definitely. But like I say, again, that's one of my research interests as well. But that is for CO2 to chemical, right, application. That is important. But in terms of climate change, it's relatively insignificant. Oh, that's important pathway, important technology, and important business. But in terms of the big picture of climate change, insignificant. Why? Because we are talking about 300 million tons of CO2 market, not even 1% of what we emitted. But this is why I say it's our scientific interest. But I think for the this is why I did not consider that in my overall big picture of the climate issue.
Right.
Thank you.
Thank you, Professor Wang. And that brings us to the end of the Q&A session.